Started. Yeah, why don't we go ahead and get going here, guys? Welcome to Wednesday. I hope that things are good. There is a homework assignment due tonight, and I'm gonna go ahead and stick with that. I haven't had anybody coming. I've noticed that my 250B students are like totally coming into my office hours, like every class every day. I'm like really busy with that. And not so much from this class. And I thought, oh, well, there's only 10 people in this class, and I've got like 85 250B students. That must be the reason. But no, seriously, there are a couple of you have been coming in on a somewhat regular basis, but I just want to encourage the rest of you, if you ever need hints or just want to talk or you need help with anything we've been going over, whether it's on the homework or not, you're always welcome to stop by. I've got more office hours today. It's just I can't have them right after class, and maybe that's part of the problem, because that would be a convenient time. But I do have a second class, unfortunately, immediately after this one. But I will be back after 8 o'clock. I will usually take a dinner break from about 9 till 10:15, and then I'm back again at 10:15, and I stay pretty late, well past 11 for sure. So feel free to stop by and ask questions, whether it's about the homework or not. I think half the class has already turned in the assignment that's due tonight. So I'm going to try to stick with that as a deadline. If that's a problem for anybody in particular, you can send me a note on the side about it, so we can kind of talk about that. But definitely just want to keep encouraging you to stay engaged with the material, with the class, with me, and we'll get through this together. We're all on the same team here. So that's one thing. And then don't forget to try to give me an idea. I think I've talked to most of you now about your papers for this class coming up. There's a few of you who I know are already going to be working in groups. I know all about that. A couple of you are still kind of not sure, and I haven't heard from a couple of people as well. So let me know what you're thinking about that as well. Try to have an idea by the end of the week anyway. Not that I'm going to make you be totally sign your life over to doing that, but at least have an idea, and we can always morph it a little bit if necessary down the road. But I would like to hear a little bit from you about that. So that is about it by way of introductions, I think. I'll have, after today's assignment, one more set of problems on the group theory stuff. And then, as you know, on Monday, I started talking about ring theory. However, it turns out that in class on Monday, I decided, I got so excited about starting ring theory that I somehow missed a page of my notes that had a really cool thing from group theory in it that I had forgotten to go over. So we're actually going to go back for a few minutes and do a little more group theory before I actually get back to the ring theory, I guess. Question, comment?
I'm just thinking, so for the final.
Yeah.
We haven't been tested on this end of the group,
True.
right? So we're gonna move forward in the ring theory. We expect to see this piece that we haven't been tested on come back in the final then?
Well, we have another midterm still too.
Oh, yeah.
Yeah, so the next midterm, it'll definitely come back. But actually, I'm always cumulative about everything anyway. So it'll anything we've covered will definitely be something you need to keep in front of mind as much as possible.
Okay.
Yeah. So yeah, good point. So far, nobody has suggested that they're going to work on this simple groups term paper idea, which I really like. So if you're still out there wondering what you're going to work on, maybe I can advertise it a little more strongly here today by reminding you about a few of the tools that we've learned for proving that groups are not simple. Remember, if a group is not simple, that means it has a normal subgroup. I should say interesting normal subgroup. Every group always has two normal subgroups automatically. The whole group and the trivial subgroup with just E. Those are always normal subgroups of any group, right? But a simple group is one for which those are the only normal subgroups, the trivial ones. So if a group is not simple, it means that it has an interesting normal subgroup. And again, the idea behind that is if there's an interesting normal subgroup, then I can break the group down into two groups that are both smaller size than the original group. And hopefully by doing that, we can understand the structure of the group G in terms of the structure of these easier to understand groups N and G mod N, right? So when groups are not simple, then we have that, we have the ability to do this, okay? This is kind of the motivation for it. And so we've been developing some tools that will show us that groups are not simple, and I've kind of been guiding this philosophy with respect to the size of the group. So certain sizes of groups can't be simple, but I did make the point that regardless of size, if a group is abelian, right, then of course every subgroup is normal, and so it's not going to be simple unless it happened to be a ZP, right? If it's ZP, then it actually doesn't have any interesting subgroups at all. Forget whether it's normal or not. Lagrange's theorem would take a group of size P and, you know, you don't have any subgroups really. So that's one case that sort of deals with the abelian groups. So most of the rest of this is more interesting for non-abelian groups. But one of the tools that we use for proving that a group is not simple is we look at the center of the group, because that's always a normal subgroup. Okay, so if it's a non-abelian group, then that center would not be the whole group, right? And if it's a prime power size group, if it happened to be that, then we also prove that the center is not trivial. So there you go. Then you've got the center being a subgroup that's not the whole group and it's not trivial, right? So you can prove that G is not simple simply by exhibiting that center. And then more recently, we've developed this idea of using CELO theory to address this problem. And I've given you at least a couple of good ways of using CELO theory to prove that groups aren't simple. One of them was that Peacock argument, where we just proved that if G was simple, then you'd have too many elements within the group. It just overflows the group in terms of just the size of the group. And then the other one, which is much more direct, is to just use the third CELO theorem, which maybe you can use to prove that there's only one subgroup of a particular size, n sub p equals 1. As soon as n sub p is equal to 1, well, then that one unique subgroup of whatever size that is always normal, okay? So these are some nice tools for proving that groups are not simple. But as I said, I sort of screwed up and I forgot a very important tool, and I'm going to put it here as number 4 in my list, which is this so-called, it's not the CELO theorem, it is something called the index theorem. I'm going to call it the index theorem. So let me state this theorem over here on this board. So this is the index theorem. This one is not stated in the book as a theorem. It's actually an exercise. So if you're looking for a reference in the book, in section 9.5, problem 18 is exactly this index theorem result. So let's state it right here. If G is a finite group and K is a subgroup of G, but not the whole group. So a proper subgroup of G. And so here's the weird assumption. If the size of the group does not divide the index of K in G factorial, okay? So if we have all of this, if we basically what this is saying is if we have a subgroup of G that's not the whole group, but which has a fairly small index. So the subgroup is pretty big, right? The subgroup would be pretty big here. Then G is not simple. So this is actually another really good tool for proving that groups are not simple. If you can find a subgroup of relatively small index, so that even after you take the factorial of that index, the size of G doesn't divide into it, then the group is not simple. This is a really, really nice result. So it was really bad that I forgot it the other day. And we'll see some examples of numbers for which we can apply this in the group work that we're going to do in a little bit today. Okay, so here's how we're going to prove this. We're going to do it by way of contradiction. We're going to assume that G is simple. So by way of contradiction, assume that G is simple. And just for notational purposes, let me actually put a box around the statement so I don't lose track of that. For notational purposes, I'm going to write the index of K and G as N. Just call that N, whatever that is. All we know about it so far is that it's not equal to 1. If the index was 1, then K would be equal to G, but it's assumed that K does not equal G here. So we're going to do that. And what I'm going to do is I'm going to create a set, which I'll call capital T. And this is going to be the set of right cosets of K in G. The set of right cosets of K in G. And how many of them are there? That's what N is, right? So the index of a subgroup in a group is exactly how many such cosets there are. And I'm actually going to write down some of those cosets. The first one, we can always just take K itself as a right coset. And then there's some additional ones. Maybe we'll use coset representatives of B2, B3, and ... up to Bn. So we'll just list our distinct right cosets like so. So we have K, KB2, KB3, and so on. Okay, so this is just setting it up with the notation. Now I'm going to do the clever part of the proof, which is I'm going to define a function f that goes from G to a symmetric group. But I'm not gonna call it S sub n, I'm gonna call it S sub capital T, because what this is, S sub capital T is the group of permutations of T. So normally when you write down Sn, when I write the notation Sn, I'm talking about permutations of the numbers 1 through n. What I'm talking about here is permutations of these cosets. Okay, there's n objects here, obviously, so it makes sense to think of this as basically being isomorphic to Sn. So there is a copy of Sn there. But instead of literally thinking of permuting the numbers from 1 through n, I just want to imagine that I'm permuting these cosets. Now, how does that happen? Well, I have to give you the formula here. I'm going to take an element of the group G, which I'll call little a, and I have to spit out as an output a permutation of T. A permutation of these cosets. In other words, somehow this element, little a, is going to create a permutation of the right cosets of K and G. And how am I going to do that? Well, it's kind of interesting. I'm going to input any right coset. I'm just going to denote it with KB without putting any particular subscript on it. And I'm going to permute it to K BA inverse. That's kind of interesting. BA inverse. Now, this KB here has to be one of these, right? And after I rewrite it as K BA inverse, this is a right coset of K in G, so it's also one of these. It may not look like it's been written that way, but it has to equal one of them, right? So this, this is just a function, right? This is my f right here, right? I plug in a right coset, I spit out another right coset. That sounds like some kind of permutation of t, the cosets of k and g. Now,
Write it KBI and be line of the indexing.
excuse me,
Can you write it as like KBI?
I could put kbi here and then this would be kbi a inverse, but it's really not necessary.
Okay.
It's really not necessary. I'll just go ahead and use a more generic notation there.
So to be clear.
Yes,
we're
please.
not sending A to KB A inverse. We're sending A to the permutation KB to KB.
Right, the outputs of f are these scrambling up functions of the right cosets. So the inputs to the function come from G. The outputs to the function are not the cosets themselves, but the permutations of the cosets, right? Each one of these permutations really could be thought of as some sigma in Sn, right? And so this is the way it's being done. Clear enough? Now, I claim that f is a homomorphism. And I'm going to try to convince you now and show you that this f is actually a homomorphism. Let's see if we can make that claim. F is, well, I definitely can make the claim. F is a homomorphism. What this means is I need to show that somehow, if I do f of A1, A2, I would like to hopefully show that that's the same as f of A1 times f of A2. It should respect multiplication. That's what homomorphism means. Well, what is f of A1, A2? It is, of course, a permutation. What permutation is it? Well, it takes a right coset KB and it outputs the right coset KB A1, A2 inverse. That's what it would spit out. Okay? So that's that. Now, what I'd like to do is start a new line and try to work out f of A1, f of A2. And make sure I get the same thing. Now, keep in mind that here, this multiplication is happening in this group of permutations. What's the operation when I'm in a world of permutations? Composition, right? So if we could even emphasize that if we wanted, there's a little composition that's going to happen there. So it's like we're doing sigma composed with tau. Of course, when we do a composition of functions, we have to remember that it goes from right to left. So over here, how is this going to look? Well, I start with KB, and I first hit it with the f of A2. So I go right to left on this, yeah? So I'm first going to hit it with the f of A2. F of A2 will take this coset and send it to KB A2 inverse. Excuse me, so that's f of A2. But then I'm not done yet because I have to compose that with the second sigma, which takes any right coset and right multiplies it by A1 inverse. So we take whatever we had before and we right multiply it by A1 inverse, and that's where we end up. Excuse me. So how do I tell if two permutations are the same? They should scramble up the cosets in the same way, right? If two of these, if I ask you, is sigma 1 equal to sigma 2? Well, I would simply be asking, does it send all of the inputs to the same outputs? These are, after all, functions. For two functions to be equal, they should send inputs to the same outputs. Right? F of x is equal to g of x only if whenever I plug x into f, I get the same result as if I plug x into g. Well, here I'm plugging A1, A2 into f and comparing it with what I get when I plug the composition of f of A1 with f of A2. So what happens here, if I do f of A1, A2, and I look at that as one of my sigmas, if I plug this right coset in, this is the answer I get out. Okay, but what happens if I put KB into the second permutation? What do I get out? Well, I get this out. Are they the same? They sure are, right? So since A1, A2 quantity inverse is the same, we know this, right? It's the same as A2 inverse, A1 inverse, then what we actually have there is the same. So because of that, right, f of A1, A2 is in fact the same thing as f of A1 composed with f of A2. And so this is that checks my claim, this is a homomorphism. It's a homomorphism. Right? Now, the next thing I'm going to claim about F is that it's actually injective as well. It's also injective. And once we get this done, we'll be almost home free. F is injective. F is injective. So in other words, I would like to basically prove that the kernel of F is just E. Well, what kind of a subgroup does the kernel of F always form in any group? Kernel of F is always a normal subgroup of G. But do keep in mind that by way of contradiction, we are assuming that G is simple, meaning that it doesn't have any interesting normal subgroups. The only normal subgroups in G, by this assumption, the only normal subgroups are E or the whole group, right? So let's just recall. So again, I'm going to explain this one. Recall that the kernel of F is always a normal subgroup of G. And therefore, since G is simple by the assumption, since G is simple, we conclude that the kernel of F is either equal to E or it's equal to the entire group, right? Those are the only two normal subgroups that would be allowed in the situation where G is simple. And 1-to-1 just means that the kernel is equal to E, right? That's what this case aligns to. So I'm going to try to convince you that this case cannot be correct. Okay, so if the kernel of F was equal to G, we are going to get a contradiction. You might notice we have not used all of the assumptions of the problem here yet. So there's some more work to still be done. Let's see if anything else is going to get used here. So if the kernel of F is equal to G, that basically means that F sends everything to the identity element. Remember, the kernel is those inputs that go to the identity element of the codomain, right? So if I'm saying that the kernel of F is equal to G, then what that means is for all A in G, F of A is the identity element, meaning that it sends KB to KB for all B in G, for every right coset. It would have to fix every right coset. Right, this is what it would mean for, for A to be in the kernel of F, then that means F of A goes to the identity element. Well, what is the identity element in the group of permutations? It's the permutation that sends everybody to themselves, right? I mean, we all know this, right? In the world of SN, what is the identity element? It's the identity element that sends every element directly to itself. So in particular, it would do this. Okay. But wait a minute, we already know what F of A was defined to do to KB. It was supposed to send it to KB A inverse. So that would mean that KB A inverse should equal KB. Okay. So that's going to give us some good information here. So this implies that KBA inverse would equal KB. This is for all A in the group and for all B in the group. For every A and B, KBA inverse would equal KB. I'm specifically going to choose E for my element B right now and just see what that would tell me. So this gives KA inverse equals K. So if we just kind of ignore the B and just say, well, what if B is equal to E? That's what we would get. And what does that tell me? If KA inverse is equal to K, does that tell me anything about the element little a? It is in K. It is in K. That is right. A is in K. So wait a minute. Does that just mean that for all A and G, A is in K? For all A and G, A is in K. That is actually telling me that K is equal to G, which is a contradiction, right? This means K equals G, contrary to assumption. Contrary to assumption, and thus we conclude now that the kernel of F is not equal to the whole group G. It's not equal to the whole group G. All right, we're getting there. Takes a little bit of work to prove this one, but the proof is actually one of my favorite results. Because at least on the extra credit midterm that several of you did, I asked, one of the questions was, what's your favorite theorem so far in this class? And I think everybody who submitted the extra credit take home either mentioned the first isomorphism theorem for groups or Lagrange's theorem. And guess what? We are going to use them both in this proof. We're not even done with the proof yet. We haven't not even used those theorems yet, but we're going to use them both. We're going to use them both, right? Let's see how this comes out. We're almost done. We are ready to take a sledgehammer and finish this proof with two of the biggest theorems in group theory, right? The kernel of F is not equal to G, so that means we're not looking at this case. So my kernel of F must be E. Right, so thus the kernel of F is equal to E. That's the only other possibility because the kernel of F is a normal subgroup of G, and if G was simple, it doesn't have any normal subgroups other than E and the whole group. But we just proved over there that the kernel can't be the whole group, right? And so now we're going to prove, well, therefore we conclude, so we're almost by process of elimination, that the kernel of F is equal to E. So guys, we've got a homomorphism, and we know what its kernel is. So therefore, we can now use Annen's version, got to get my name in here somewhere, of the first isomorphism theorem. Ready for this? By Annen's version of the, oh, and by the way, notice we have not even used all of the assumptions yet. This thing hasn't even been mentioned yet. It must be coming. It must be coming. It's coming right around the corner. Oh, I'm so excited. By the first isomorphism theorem, G mod the kernel of F. What was it? It's isomorphic to F of G, right? That's how the Annen's version of the theorem is stated. But the kernel is E. The kernel is E, so that just means that G is isomorphic to F of G. I'm still hunting for a contradiction. Now, F of G is always a subgroup of whatever the codomain is. The codomain of my function F over here is S sub t, right? Is S sub t, which, as I pointed out over there already, is actually isomorphic to Sn. So if I just kind of read between the lines here, guys. G is essentially isomorphic to a subgroup of Sn. What do you suppose I'm gonna do with that?
Lagrange's theorem.
I said both of those two big theorems are gonna get used. We've used the first isomorphism theorem. Now we're saying G is a subgroup of Sn. That means the size of G divides the size of Sn, right? So by Lagrange's theorem. I think I'm gonna have to have this on the final exam. I mean, look at how much of group theory is used in this proof, right? So now we're using the Lagrange's theorem. The size of G divides the size of Sn. What is the size of Sn known as? Or what is it equal to? N factorial, right? But guys, N factorial is this thing. This is this thing. We were assuming that the size of G does not divide that thing. The size of G does not divide that thing. So, I'll just finish it right here. The size of G divides the index of K and G factorial, and this is a contradiction. So we're basically in trouble no matter what we do. If the kernel is equal to all of G, we get a contradiction over there. If the kernel of F is equal to E, we get a contradiction over here. And that's the only possible scenarios. And so this group can't be simple. So thus G is not simple. And I'd like to show you, well, first of all, are there any issues? Anybody's a little stuck on anything here? Yeah, Nikolai?
So for a group to be simple, the only normal groups are E and the group itself.
True.
Does that mean that if earlier on we showed that it can't be G itself, the only possible normal group is E?
Right.
So that, wouldn't that just automatically break that it's simple, or is it possible for a group to be simple without one of the two?
No, you have to have E being a normal subgroup and you have to have the whole group being a normal subgroup. Those are the two options. So your kernel of F has to be one of those. And I prove that in either case, we end up getting a contradiction.
Gotcha.
Yeah, there's a ton of stuff in this proof that is really, really useful to understand. And I would now like to show you that we can disprove simplicity of groups using this tool, right? So here's an example just to apply it, and then I'm going to let you guys try in some group work to do a couple more examples. Prove there is no simple group of order 24. No simple group of order 24. So for the solution here, you know, the size of this group G would be what, 2 cubed times 3? For a group of size 24, okay, I don't necessarily know that it's abelian. In fact, it doesn't have to be abelian. So I don't know anything about the center necessarily. I'm trying to think about our other tools. Could we have proved that this is not simple without this theorem? So the center of a group of size 24, I don't really know anything about it. What about the CELO theory? What about the CELO theory? The number of CELO 2 subgroups, well, it has to have the form 1 plus 2k, but then has to divide 3 for some integer k. And it'd be great if we could say that n sub 2 equals 1, then that subgroup would be normal and G would not be simple. But unfortunately here, this implies that n sub 2 is equal to 1 or 3, could potentially be 3, right? What about n sub 3? Well, n sub 3, well, that's 1 plus 3k, or 3l, I'll use a different letter here. That has the form 1 plus 3l and has to divide the rest of the number of, for 24, which would be 8. This is for some L in Z. Well, and also we aren't able to get the immediate result that n sub 3 is equal to 1 either. So n sub 3 is either equal to 1 or it's equal to 8. Now, we could try to do the peacock argument of counting elements here. The only thing is that's a little hard about that is that the CeLO 2 subgroups, which have size 8. So guys, you remember when we do the peacock argument, we're trying to draw these feathers, right? And you have E here and they have all these dots here. As long as the sizes of these subgroups is prime, then the feathers can't overlap. And so you literally do get P minus 1 elements there, P minus 1 elements there, P minus 1 elements there, and so on. You can start accruing the elements quickly. But my CeLO 2 let's say I had 3 of them. If I had 3 CeLO 2 subgroups, right? I could have my first one here. All right, so I have 7 non-identity elements, that's fine. But the second feather, because this has size 8, Lagrange's theorem does not forbid me to have an overlap of maybe, there could be like 4 elements total there, and then 4 more out here. And then there could be 4 more out here. I'm not going to collect the elements as quickly as I would like. Remember the one on the group work on Monday? We were like quickly able to get whatever it was, 360 elements of whatever order 19 or something like that, right? If it was a prime number, it works great. But like feathers of size 8 is problematic because I don't know that the elements or that the feathers are all non-overlapping. So these counting arguments can get tricky when your CeLO subgroup doesn't just have a prime size. So that can be a little bit of a problem. I don't know that I'd ever actually sort of made that observation. Just be a little careful with that. But so we could try, you know, I still am not convinced that the peacock argument wouldn't work here. We could focus on the n sub 3 being equal to 8 potentially. Yes.
Could n sub 3 also be 4?
Oh, you know what? That's supposed to be a 4. Oh, I'm so sorry. Yeah, this is supposed to, I'm sorry, that was supposed to be, it can't be actually equal to 8. It would have to be equal to 4. That's exactly right. Was that your point?
Yeah, I was
Oh.
like, are you doing like -9?
No.
Eight.
Total typo on my part. I'm just trying to see if anybody's awake out there. Right? So if people aren't catching my mistakes, it's always on purpose, of course. So, yeah, no, I meant to write 4 right there. Yeah, so, you know, it's a little problematic getting more than 24 elements in this group because if the feathers overlap a little bit, you don't gather as many elements as quickly to sort of overfill the group. Okay, but you're ready for the really fast answer to this problem? I do know that there must be a CeLO 2 subgroup in G. They always exist, right? The number of CeLO 2 subgroups, as you can see, is at least 1, right? So now we're going to do the solution. Let P sub 2 be a CeLO 2 subgroup. It has to exist, right? If it's the only one, then of course it would be normal, but we don't know that. So just say, let's just take one, but I'm going to note what its size is, which is 8. And so the index of P2 in the whole group, of course, this will be 24 divided by 8, which is 3. So what do I have here? I have P2, which is a subgroup of G. P2 is not the whole group G. Its index is 3. And so the size of the group being 24, that does not divide 3 factorial, right? So since 24, which is the size of G, does not divide 3 factorial, G is not simple by the index theorem. All right. So there you go. We have found another tool that can quickly show us that our group is not simple. I really like that theorem. Yeah, that's it.
In the proof of the index theorem, you basically proved Cayley's theorem. Right?
It's very closely related to Cayley's theorem. Any group can be embedded as a subgroup of a suitable size symmetric group. Very true. Yeah. I would say it's not quite the same thing because here we're doing permutations of the cosets of a group. Cayley's theorem is literally done on the raw level of elements. For those of you who have seen Cayley's theorem, it would essentially be Cayley's theorem is basically when K is equal to E. So the actual, raw version of Cayley's theorem, you just put E here. So this would literally be the order of G factorial here. Yeah. But yeah, it's totally a similar idea. You essentially take an element out of the group and you associate it through the function with a permutation of the elements of not the cosets, but the elements of the group. Absolutely. Absolutely. Yeah, great. Okay, so let's go back to ring theory. I just had forgotten to do this one on Monday. And I went down to my office the other night and I was like, oh my God, what have I done? I've got to make sure these people get to see the index theorem, and not only because of how useful it is, but also the proof is actually very instructive. So I really like it. Is that a hand, Avery?
Yeah.
Please.
Just quick reminder, the size of P2 is 8 because it's 3 divided by 24.
Okay, so the size of a CeeLo P subgroup is always just whatever the largest power of P is that divides into G. So you're just grabbing off the largest power of 2 in this case, for a CeeLo 2. A CeeLo 3 subgroup in this case would have size 3. Yeah, that's right. The size of the CeeLo P subgroup is just P raised to the power of the maximum number of powers of that element, or of that number that divides into G. Beautiful. Okay. Great. Okay. Well, with that group theory in the rear view mirror, now we will practice that in some group work in a few minutes. Question first.
Bit of a side tangent question, I'm just trying to recall.
No worries.
The kernel being E, making it a injective, does that also require homomorphism?
That does require the use of homomorphism to
Okay.
prove that, which we, of course, are almost always in that situation. When we're in a group, we tend not to work with functions unless they're homomorphisms.
Just trying to
So-
recall.
Yeah, and it works that way in every context. So same thing's true for vector space linear transformations. If it's not a linear transformation, then injective and kernel of the transformation equaling the zero vector doesn't work. Yeah, so good point. Okay, guys, let's go back to the. Oh, Jason.
Oh, sorry. We just 6 not divided by backwards.
You got it backwards. This number does not divide 6. So it got the 6 is not a multiple of 24. Yeah, exactly. I'm glad I'm not the only one who gets mixed up by that. I think you even confessed that
Oh, yeah.
this A divides B thing. Whoever came up with that notation, I don't know. I'm gonna go complain to Dr. Lyons. Oh my gosh, okay, anyhow, so yeah, we gotta get that part straight. Okay, anything else that I should clear up before we go on? Okay, great. If not, let's just go back to our start of our conversation about a ring theory. So I'm gonna go back to the ring theory and kind of remember where we were on Monday before we left off, and then we'll pick things up a little bit from there. So we've been talking about, so here's my ring R. This is kind of like a quick recap again. You have to have a 0 element in the ring, of course, because under addition, a ring forms a abelian group. The ring does not have to have a multiplicative identity element, but if it does, we would write it as a 1. And a ring does not have to have, the elements do not have to have multiplicative inverses, but if they do, we can draw them inside of the ring here. And these are going to be denoted as the units of R. I'm not sure I officially wrote that down last time. So maybe I'll add this right here as a quick definition and to make sure that it is in our notes. So if we take an element A in the ring, and if A is multiplicatively, such a big word, multiplicatively invertible. Remember, additively invertible is not even an issue. In a ring, every element must be invertible under addition. There has to be an additive inverse because it forms a group under addition, and groups have to have inverses. But under multiplication, this is an if, right? The element might have a multiplicative inverse. And if it does, we call we call it a unit of R. Excuse me, a unit of R, and then notationally, the units of R are denoted as U of R. So that's what I've shaded in on my little diagram here, the units of the ring. And it's worth noting that U of R under multiplication forms a group. Yeah, so it ends up forming a group, as it turns out. Is that clear why it forms a group? It obviously has one in it. That's your identity element. One of the axioms of a ring was that it had to be associative under multiplication. If we remember from Monday, I wrote down that big list of the rules of a ring. And one of them was that if we just focus on the multiplication, it has to be associative. So this is an associative structure that has an identity element, right? And everybody has an inverse because that's the definition. If A belongs in this set, then it has an inverse, right? It's multiplicatively invertible, so it's closed under inverses. And then what else do we need? We just need closure under the operation. Well, that's also true because so closure under the operation being multiplication. Well, if you multiply two units together, the result still is something that has an inverse because we can just figure out the inverse by taking the product of the individual inverses in the opposite order. So this is a very sketchy, it's not really a proof, just something to kind of get you thinking about that, but it's certainly going to be closed under the operation as well. The product of two units is a unit. AB is a unit because it has an inverse. That inverse is not only, we can say it has an inverse, but we can also literally write down what the inverse would be. And that's like the best way to prove something exists is to literally exhibit what it is. So that's what I've done right there. Yeah. So this forms a group, and we've already seen some examples of this because, as you know, Zn is a ring. And the units of Zn is literally just that group, and it was on there on both the midterm and the midterm redo, which is the U of n. Those are the multiplicatively invertible elements of Zn. That's right, and this forms a group under multiplication, right? Great. Yeah, so that's a nice example. By the way, I don't know if I've mentioned this, but if n is a prime, you might have noticed on the midterm it was a prime, it was Z11. And then on the redo midterm, it was another prime, which was 17. I did that on purpose. It's because whenever you take the group of units of a ZP, you always get a group that is cyclic, actually. So there's nothing obvious that says this has to be a cyclic group over here. Just because Zn is cyclic under addition doesn't make the multiplicative group of units a cyclic group necessarily, but it turns out that it is. It's worth making a note of that. That is not an obvious fact by any means, so I won't pretend to have a proof offhand right now. But if n is prime, then U sub n is actually a cyclic group. And on the exam, I just wanted the group to be cyclic because you're being asked to create a homomorphism, and it's just easier to do, or an isomorphism, which is easier to do if it's already cyclic to begin with. Okay, great. So that's the picture so far. Questions on anything yet? What do you think? Makes some sense? towards the end of class on Monday, we added another layer to our picture here because we started talking about the zero divisors, and we can draw those on the picture here. I'll do this in red, the zero divisors. And I'm drawing them up here to not overlap with the units, and that's because they can't overlap. You cannot have an element that's both a unit and a zero divisor. So let's come back over to this other board where I have a little bit more room to talk about the zero divisors really quickly. This out of the way. Oh, I hate erasing this proof. It's like my favorite proof. You guys do anything when you hear your professor say, "Oh, that's my favorite theorem," or "Oh, I love that proof." Do you like put a little star in your nose? Make sure that we study this one, right? Yes, cool.
I was gonna ask, I've seen in other books definitions that include zero as a zero divisor.
Generally, okay, I would like to know what books those are.
Okay.
It is pretty standard to not allow zero as a zero divisor.
Okay.
Yeah, so I think the way I've drawn it by keeping the zero totally out of that bubble is more of the standard way it would be understood.
They basically have to put for any zero divisor besides zero. And the
Yeah,
rest of their
and then it's a hassle to have to say that for every result that you have. Exactly. So just recall here, guys, again, this is just reviewing again, a zero divisor A in a ring is any non-zero, okay, we'll go ahead and emphasize that now. Any A non-zero such that there exists a B not zero with A times B equals zero. And I have mentioned that you can define zero divisors for elements in non-commutative rings. Our book likes to just sort of make the assumption, for the most part, that the ring will be commutative under multiplication. If it wasn't, then you might have to worry about also having B times A equal to zero as well, but we don't have to do that here. Right, so then now I'll make a couple of remarks, and hopefully these will be fairly clear as well. A zero divisor cannot be a unit. So you can't be both. You basically can't be both. That picture over there shows exactly the relationship between the two sets. And I guess I should say, and conversely. Right, so a zero divisor can't be a unit can't be a zero divisor. They're totally non-overlapping collections of elements. It is possible to have elements that are neither zero divisors nor units. So it's possible to be neither. Can anybody think of a ring where there's an element that's not a unit, but it's also not a zero divisor? Miguel?
Integers like 2 is not a unit.
Okay, love it. Yeah, just take the integers. You can also use Zn as long as n is not a prime. And you could just say something like the element A equals 2, right? Because it's not a unit. The inverse under multiplication doesn't exist in the integers, but it's also not a zero divisor. So A equals 2 is neither a unit nor zero divisor. But then we talked about, I'll make another definition here. What a field is a field is a ring such that a commutative ring with one, such that every non-zero element is a unit. So a field is a commutative ring with one such that every non-zero element is a unit. And so your picture, in the case of a field, your picture looks like this. You have 0 down here, right? 0 down at the bottom of the picture, but then everything else forms U of R. So again, those examples on the sample or on the first midterm, right? Z11. Right, the units was everything from 1 through 10. In Z17, the units were all the numbers from 1 through 16. So in this case, because the units take up so much room, there's no room to have any 0 divisors, right? And I think we wrote this down last time as well, but just to write it down one more time, if you have a ring with no 0 divisors, it is called an integral domain. Exactly. So I'll just again recall this definition as well. So many definitions, guys, at the start of ring theory. Just have to kind of make some flashcards or get in the flow with this. But a commutative ring with no 0 divisors is called an integral domain. An integral domain, exactly. So essentially, if you have a field, since everybody is a unit, there's no room to have any 0 divisors because you can't be both, right? So basically, this proves theorem 3.8. Theorem 3.8, which is basically just proved from the definitions, which is that every field. This I don't think I actually wrote down last time, but you probably already know this. I just want to get it back up here again. Every field is an integral domain. Cole, did you have a question?
Yeah, last time you mentioned that you could just take out commutative and it still works. It's the part of the definition.
For the integral domain definitions,
So
yes.
that would
You
make-
can't do that so much for fields. The field
Yes.
is required to be commutative, but yes.
So you could then theorem 3.8 would be that every division.
Division ring is a domain.
It's okay.
It's usually they just write the word domain. They don't say integral domain.
Okay.
Yeah, but yeah, it's the same definition.
Do you also, do you only call it an integral domain if you have the identity too? I thought that was the case.
I should be adding that back in there. It's so hard because different authors do different things. A commutative ring, with 1. Yeah, we can add the identity element there as well. It's totally okay. Most of the time, most of the rings we work with will have 1, so it's not a big problem. Larry?
Right, so that one in the definition for field is all identity.
Yep, that's this is also the identity of the ring there, exactly. Yeah, exactly. It's a commutative ring with 1. I should just add that everywhere. It would be the safest way to do this. Just so you're aware, of course, theorem 3.9. So this theorem doesn't even really need a proof. It's pretty much automatically a consequence of this remark here. The remark needs a proof, but I'm not going to do it. The converse of this theorem, however, is not quite true. It is not true that every integral domain is a field. And in fact, we have a wonderful example right here. The integers is an integral domain, but I have elements that don't have multiplicative inverses, such as the one Miguel gave me, which is a equals 2. So it's not true that every integral domain is a field, but does anybody know a way to salvage the converse of the theorem? And I know that you know, because you were proving it on that board there on Monday. Yes, it was. Yes, it was. You were right. You didn't know it. You were writing down the proof on that board. I was talking you through it. You know what it is?
But then my boy Miguel like figured out.
We could let somebody else. Does anybody else have an idea what my converse statement is here? It's not true that every integral domain is a field
Is it the
unless.
units of an integral domain are fields?
No, it's not what I was looking for. What was that?
The finite integral domain.
Finite is the word we're looking for. Yes, Miguel saves the day. Yes, every finite integral domain. Every finite integral domain is a field. Okay. And I'll use one of my favorite proof techniques for this one. Actually, I'm gonna let you guys prove it in the in one of the group works that we're gonna do. Maybe not the one we're gonna do today, but we'll do that soon. So I'll put a little note here, group work number 7. I'll have you guys do it. It's not that hard. It's not that hard. You start with some non-zero element A and you want to prove it as a multiplicative inverse. Well, what you can do is start taking powers and powers and powers of A, right? This is what you're doing the other day. The A squared, A cubed, A to the 4th, A to the 5th. And if it's finite, then 2 of those powers have to be equal, right? So A to the I equals A to the J, right? Where I is greater than J. And we're not in a group anymore, so we can't like do anything with multiplication, but I can subtract because I'm in a ring, right? And then I factor it. Remember this? Yeah. So then you factor it and you prove that there's an inverse for A out of all that. Anyway, I'm doing the problem for you now. I get excited. You have to forgive me for that. Okay, one more thing here, guys, before we take a break today, and then we'll be in a good place to come back from break and do a little bit of group work together. I want to just quickly put down the concept of a subring, which again should be mostly just review, and it works just the same as it does for groups. So we won't dwell on this other than to maybe give a couple of examples. Okay, so let me come over here, and this I did not get to on Monday, so I will try to write some decent notes here for this part of it. But subrings, as you know, it should just be a ring inside of a bigger ring, right? It's a ring in its own right, living inside of a larger ring. So here's the quick definition. Let R be a ring. This could be any kind of ring, commutative or non-commutative, with identity, without identity, doesn't matter at all. So just any ring, a subset S inside of R is a subring if it forms a ring in its own right. If it actually forms a ring in its own right. And so you probably know what's going to happen here is that most of those ring axioms that are already true for R by assumption would then get inherited by S. So things like associativity, the distributive properties of rings, that's certainly going to get inherited. The fact that it's got to be an abelian group under addition, it's really just going to be a subgroup of an abelian group under addition. So that makes it still an abelian group under addition, right? So all of that stuff will be easy. The only issues here will, of course, as with groups, be the closure requirements. And there is a theorem then that, of course, basically spells that out, and I'll state it here for you. 3.2. S is a subring of R. This is how you actually prove it. If and only if S is a subring of R, if and only if S is closed under, well, 3 things. First of all, it has to be a group under addition, so it should be closed under addition. But even to be a group, the structure has to be closed under the operation as well as inverses. Now, the inverses for the addition would be additive inverses. So I'll write additive inverses here. And then thirdly, the new part for a ring would be the multiplication. And so it needs to be closed under multiplication. That's right, closed under multiplication. Now, a lot of times what we do, or what you can do if you would like, and some of you have been doing this even in the group theory, which is fine. You can kind of combine addition and additive inverses into a single verification, which is that you simply have to show closure under subtraction. It can basically just get away with that. So you have an alternative, which is you can do, instead of addition, additive inverses, and multiplication, you can just do subtraction and multiplication. See, if you check subtraction, that actually also checks addition. Because if you know, A minus B that's just A plus negative B. So if you've checked additive inverses and addition, that's equivalent to checking subtraction. Especially,
Doesn't subtraction also get multiplication, right? Because you're multiplying by a negative?
it's not really multiplying by a negative. It's, I mean, it's going from A to negative A. I guess you could think of that as multiplying by -1.
Yeah.
But that's not a general multiplication of A and B. Right? So there's other numbers to multiply besides -1. So we have to do, we really do have to check fully the multiplication and the subtraction. Cool. And then Miguel?
This also requires that S is a subset of R.
Oh, yeah.
That
Oh, yeah.
S
Yeah,
is
yeah, yeah.
not empty.
Yeah, I'm sorry, yeah, all that stuff. Some people are very fussy about putting those words in their definitions, I've noticed, but for me, it's like, okay, if the thing is empty, let's just go home. And I mean, what are we here to talk about, right? So I don't even tend to write those kind of words down. Yes, S should be a non-empty subset, because you could argue that if it's the empty subset, then everything is true, right? Because, oh, I've got to check closure under addition. Let's assume we have two things in the set. Oh, wait, we don't have two things. So we can't even do that, right? It's like, so therefore it's vacuously true. Okay, well, that's like me saying that I'm going to throw a party every 8th day of the week that exists, right? Well, we never get to the 8th day of the week. So whatever I'm going to say after I'm talking about the 8th day of the week is totally irrelevant and never applies. So why bother to even breathe another moment on that topic? You had a question.
Could you combine those two into like some sort of like distributivity? So like if you have like A times B minus C.
I see what you mean. So A times B minus C, if you could show closure under that. I certainly think that you could, because you could imagine here, if A was equal to 1, you'd get the subtraction. And if C was equal to 0, you'd get the multiplication. So checking that it's closed under that would subsume both of these. I don't want to do this though. It's too much room. Let's check these two things separately. Yeah. Okay. You guys are full of good ideas today. I love it. Oh, this is so much fun.
Empty set's not a ring because it doesn't have a identity element.
Which one?
Empty set's not a ring because it doesn't.
Right.
have a-
Right. It doesn't have the identity element anyway. So, right. I mean, if your set is empty, there's just nothing to talk about. But yeah, people get a little bit bent out of shape over it and they're like, oh, you didn't state that it was non-empty. I have a couple of professors in mind right now, but I won't mention who they are. Okay, so let's do a quick example of this and then we'll take a short break. So an example of something where we would have a subring. So we could let the ring R be literally the real numbers R. Okay, so then we could let S be what is written as Z of the square root of 2. And this is actually going to be sort of the construction of this is that it's the smallest ring that contains all of the integers and contains the number radical 2. If you think about what that would look like, you basically would have all expressions of this form, A plus B radical 2, such that A and B are in Z. And then the claim here, the claim is that S is a subring of R. S is a subring of R. And so just to practice this once, and I know this is something probably you've done it before, so we won't spend long on it. But closure under subtraction, right? You would just take two things that are in the set here, let A plus B radical two and C plus D radical two both belong to Z of radical two. And this would be where A, B, C, and D are integers. So we just have to set up all the notation. And then if we subtract them, A plus B radical two minus the quantity C plus D radical two. I just have to make sure that this is still in the set S, which really just amounts to writing the form of it. It needs to be in the right form. So I'm just gonna subtract these two guys and I'll get what? A minus C and then plus B minus D radical two. And that is an element of S. And for the people who really like to justify every single last little thing, this one I can almost let you get away without it, but I'll add it there that the A minus C and the B minus D have to still be integers, which they are. And so we have an element of S there. And then lastly, the closure under the operation, the multiplication operation, I should say, right? I'll just pick up where I left off and I'll compute A plus B radical two times C plus D radical two. And what we have to do here is, again, figure out what it is and then express it in the form of something out of the subring Z of radical two. So the way you would do this one, guys, I'm going to quickly FOIL it for you. The first and last terms gives you a integer, which is AC plus 2BD. And then the outer and inner terms gives you AD plus BC times radical two. And again, this is in S. And again, the reason is just because this, I guess I'll write it down this time. If you didn't write this down, guys, I would not dock you for it because it's just really obvious. But at least one time I will write it fully down the definition of that. Right. This isn't just a subring of R. It turns out it is also an integral domain. So the real numbers are a field. The inside of that field, we have this subring. It's not necessarily, this is not a subfield. I probably should write down the definition of that as well. I'll do that after the break. But the subfield also has to be closed not only under subtraction and multiplication, but if I want to have a field, it's going to need to be closed under multiplicative inverses as well. So there'd be an extra requirement. And this won't be closed under multiplicative inverses because even just the integers are not closed under multiplicative inverses. So even some of the obvious elements of S fail to have multiplicative inverses. So it's not going to be a subfield, but it does manage, maybe I'll write it down, it does manage to still be an integral domain. So I'll just make a quick remark here and then, so S is also an integral domain. Is that obvious? I think it is. Guys, if there were zero divisors here, then those zero divisors, of course, also live in the superring that contains them. And then the real numbers would suddenly not be an integral domain. Well, we know that the real numbers are an integral domain. So therefore, S would also be an integral domain. So it's almost like this is another thing that gets inherited, right? All those axioms of a ring get inherited, but then the property of no zero divisors is getting inherited by S as well. So it's a fair thing to say. But S is not a field. Yeah, it's definitely not a field. Question?
I've seen that notation, bracket root two, or maybe Z bracket X. I've heard it read as Z adjoined root two.
That's fine.
Yeah.
Yep, that is also totally okay to say it that way. definitely. Nikolai?
Is there any, notation for subrings like we did with subgroups? where-
But the less than or equal to, you know, that is not as commonly used in ring theory, believe it or not. So you'll see me writing, it's a great question. You'll usually see me write out the words S is a subring of R most of the time. If somebody ever did write that down, I probably would know what they meant by it, but it's generally not as common to see that notation here. And same thing with normal subgroups. We're gonna have something that's equivalent to normal. So you might, that should be everybody's burning question, right? Okay, so we know what subgroups are in a group, and some of them are special because they're normal. Now we have subrings of a ring. Are some of those special in ring theory as well, so that we could form quotient rings? Well, of course we're gonna do that, right? This is not a big surprise. So anyhow, I think we should take a little break. It's 5:15. Let's take a break, and when we come back from break time, we will also do some group work together, practice a little bit. So I'll see you guys in about 10 minutes.
They are.
I think it's literally said, like,
I can't tell. I'm like, did you pre-solve that?
This was all cash outlets.
yeah, but no, because that system, and then just the way it's, I'm like, oh, this is.
Funny, it's like,
It's great, yeah.
probably.
It's not a similar one, but it's more subtle.
All right, guys, maybe I'll go ahead and get back to what we were doing just a few minutes ago. I do have this group work. I want to give you a good 15 minutes to work on it. So I'm going to try to only talk for less than 10 minutes here. I just want to wrap up so that next week we can get what we're going to do. Starting next week, we'll go right back into homomorphisms and isomorphisms for rings. So we're kind of, this is one of those things where you just take everything you did for group theory and you try to like redo it for ring theory as best as you can. And some things work really easily, very naturally, other things not so much. So we'll be following that program here in the next few weeks. But we had just talked about subrings, and I thought, well, I might as well talk about the definition at least of a subfield and maybe give a quick example of that. And then we'll call it a day as far as the new material goes. But of course, if we're going to talk about a subfield, then technically we're going to have a large field F to begin with. So let capital F be a field. Okay. Then a subset. And the book doesn't want to use a G, obviously, for that. So we'll use an F prime, which is a subset of F. So if a subset F prime of F is a subfield of capital F, if basically two things are true, right? First of all, F prime is a subring of F, so it has to be in and of itself already a ring. So it'll inherit most of the algebraic axioms from the field F, right? It'll inherit those. So then we're already assuming now that it's also closed under subtraction and multiplication. Those are the two things we have to have for a subring. But one more thing that it needs to be closed under, it needs to be a subring of F, and then it needs to be closed under multiplicative inverses. So if F prime is a subring of F and is closed under multiplicative inverses. Now remember, everything in F prime will have a multiplicative inverse, other than every non-zero element will have a multiplicative inverse in the big field. The issue is that that inverse needs to actually belong to the F prime, the subfield, right? So closed under multiplicative inverses, together with being a subring, that makes it a subfield. So in other words, just as a remark, F prime is a subfield of F if and only if, I'm not going to write down non-empty, just going to say if and only if F prime is closed under closed under, first of all, subtraction. And then secondly, multiplication. It's closed under subtraction, which makes it an additive abelian group. Then it's closed under multiplication, which makes it a subring. And finally, third point now is it needs to be closed under multiplicative inverses. Right. So every non-zero element of F prime has to have an inverse that's actually in F prime. So, a great example of this, a great example of a subfield that's kind of obviously Q is a subfield of R, which is a subfield of C. Those are all fields, right? One inside of the next, inside of the next. But if we wanted to give something maybe a little bit more interesting, well, maybe I'll go ahead and write Q down. But I'm going to do one more here where I'm going to do Q adjoin radical 2, which is inside of the real numbers, which is inside of the complex numbers. This is a chain, excuse me, of subfields of C, complex numbers. Yeah. And just so it's clear here, the interesting one is this Q of radical 2 or Q adjoined radical 2. This is exactly what you think it is. It's the set of A plus B radical 2. But now A and B are allowed to be rational numbers. And if you want to have closure under multiplicative inverses, you'll need to allow A and B to be rational numbers. Did you have a hand up?
I did.
Okay, sorry, what's up?
Could you also do the same thing with B and C and say that it's closed under division, or do we like to avoid the term division?
Let's see. Yeah, I think it would be better to keep these two split apart as well, although that would be legitimate to say it that way. Yeah, closure under division would include, it's the same kind of way that subtraction combines addition with additive inverses. This division would combine multiplication with multiplicative inverses. This tends to be the way it's generally laid out, though. Yeah, so, but good point. That's a very good point. Right, so, here, this thing, why is it closed? So it's clearly closed under subtraction and multiplication. The only one that's a little bit interesting is the multiplicative inverses. So closure under multiplicative inverses, I'll just tend to write it this way. This just would be that, well, we have to look at A plus B radical 2 inverse under multiplication. And make sure that this inverse, which it definitely has an inverse in the real numbers somewhere. But I need to know that it has this form again. So the way that you do this, does anybody know how I'm going to prove that this thing has an inverse of the same form? Yeah, exactly. You actually, this is a little trick, right? You multiply on the top and the bottom by what's called the conjugate of that element, which is A minus B radical 2. Because what'll happen is that the denominator will get substantially cleaned up. It becomes just A squared minus 2B squared on the bottom, which is certainly going to be a rational number. And then the numerator becomes A minus B radical 2. And so then you can split that up, or you can just rewrite it basically in a manner that looks like something from Q of radical 2. Right, so it would look something like that. And so this belongs to Q of radical 2, as long as the coefficients are rational. The only worry here would be, could these denominators be 0? Because then the expression doesn't make sense and you haven't technically found an inverse under multiplication for this element. So we should make a quick note here that A squared minus 2B squared is not equal to 0. And how do I know that? I will actually prove that. Gonna get really formal about it. So, by way of contradiction, right? So if somehow that was equal to 0. Okay, so you guys have probably seen these kind of things before. It's not something I need to go too slow with. But if it was somehow possible for a squared to equal 2b squared, well, then what would happen is the square root of 2 would be a over b. And A and B are rational to begin with, because that's what we're starting with here in the beginning. Right, so way back in the beginning here, A and B are definitely rational numbers to begin with. And so, of course, you divide these two rational numbers together, you get a rational number. This would be an element of Q. And now you just observe that that's a contradiction to the fact that the square root of 2 is not rational. So a contradiction, since the square root of 2 is not rational. Do people all feel comfortable with that at least? If you had to prove it, you'd go to Math 430 and say, well, I'll assume it's rational. I'll clear denominators. I'll have an integer equal to an integer. I'll look at the prime factorizations and I'll have the wrong number of factors of 2 on one side. There's a uniqueness to factoring a number in terms of primes. And so like if you actually, so you could just go back to here, right? If you think about factoring this equation into products of primes, every prime that shows up on the left side will show up an even number of times because it's going to be squared, right? But then on the right side, the prime 2 shows up one time here, and then an even number of additional times over here, which would mean that the 2 is occurring an odd number of times on this side, an even number of times on this side, and that violates the, what's it called? Fundamental theorem of arithmetic, which I hope they're teaching you in Math 430. Right, so that is a really, really fundamental idea. And so right, so the square root of 2 is not rational. We can safely assume that in this class. And so therefore we would have a contradiction here. Also, I should point out the B cannot be, you might be looking at this saying, well, what if B was 0? Just B. But see, if B was 0, then A would have been 0. And as soon as both A and B are 0, now you're trying to find an inverse of an element that doesn't have to have an inverse under multiplication, which is 0 itself. So you don't have to get too far into the weeds on that one. Okay, are we okay with this? So this is closure under subtraction, multiplication, and now multiplicative inverses. That's enough to really prove that this Q of radical 2 is in fact a subfield. One of the big themes of this class is going to be later on that we're going to be taking fields and breaking them down into subfields. Or we can turn it the other way around and view the larger fields as what are called field extensions of the smaller fields in the base. And that field extension theory turns out to be, as I've kind of been hinting for a while now, the field extension theory turns out to be highly related back to group theory again. And to basically to every field extension, anytime I have one field inside of another, we are going to associate a group to that extension. It's called the Galois group of E over F. So that's coming soon enough. After spring break, you'll have to come back after spring break. In my soap opera lecture style, I'm going to make you wait a little longer. Anyway, it's coming. It's really good stuff. Okay, I think that was about all I wanted to do with this little section on subrings and subfields. Just what are the closures you have to verify? I think that's about all I got to say on that. Any questions? You guys have been great. Lots of great questions today. I really appreciate it. Let's take the last few minutes and try. This is group work number 6. I know we did a lot of group work on Monday. Today, this is a little quicker session, but I bet that you can get at least a little bit of it done. It's totally right on topic with what we've covered today. So be sure to use your notes to help you if you need to, since I know it's all really super, super fresh. But I will come around and give you guys a hand. So have at it. You can erase anything. You can go anywhere you want. And we'll do some group work.